topic of today is Naïve Bayes algorithm. My name is Johan Hagelbäck and I'm a senior lecturer in computer science at Linnaeus University. There are several algorithms we can use for classification tasks, supervised machine learning. Artificial neural networks, support vector machines, k-nearest neighbor, decision trees, and many more. And here we will focus on a basic but quite common algorithm, Naïve Bayes. It has several benefits such as high speed and is often very effective, for example, text classification problems. To get started, we need to learn about Bayes' theorem. It describes the probability of an event based on prior knowledge of conditions that might be related to the event. So Bayes' theorem is stated using the following formula. PA given B is equal to probability of B given A multiplied by probability of A divided by probability of B. So this P A dash B shall be interpreted as probability that A occurs given B, and is best explained using an example. We are interested in knowing if a stiff neck is a good sign of being a good FIFA player in the FIFA video game. To answer this using Bayes' theorem, we need to know the prior probability. So we can measure that 50% of the good FIFA players have a stiff neck. So the probability of stiff being good is 0.5. 1 in 50,000 players is good at FIFA, so probability of being good is 1 in 50,000. And 1 in 20 players suffer from a stiff neck, so probability of being stiff is 1 in 20. So we can now use these prior probabilities. Probability of being stiff given good 0.5, probability of being good 1 in 50,000, and probability of having a stiff neck 1 in 20. So and we can use these to calculate the probability of being a good FIFA player if you have a stiff neck. So we just put in our values in Bayes' theorem. So probability of being a good FIFA player if we have a stiff neck is equal to probability of stiff given good multiplied by probability of being good divided by probability of having a stiff neck. So we put in our numbers here and we calculate and we reach a number of 0.0002. So given these prior probabilities, we can use Bayes' theorem to say that the probability that a player is good at FIFA if he has a stiff neck is 0.0002, or roughly 1 in 5,000 players. So even if 50% of the good FIFA players have a stiff neck, it's not a very good indicator of being good or bad at FIFA. The problem with Bayes' theorem is that it only takes one attribute into consideration, a stiff neck, when calculating the probability of belonging to a specific category of being a good FIFA player. And in most real-world applications we have more than one attribute: stiff, bad neck, having a good gamepad, having a high-resolution TV with a large screen, etc. All things that have some effects of us being a good FIFA player or not. So we need a way of combining several inputs to get a probability of belonging to a specific category. And this is handled by the Naïve Bayes algorithm classifier. The classifier is called naive because it assumes that the attributes are independent of each other. It means that the probability of one attribute belonging to a specific category is completely unrelated to the probability of other attributes belonging to that category. So there are no relations between attributes. And this is actually a false assumption for most tasks. For example, money is a better spam indicator if we were to indicate spam emails if in combination with casino than with programming. The independence between attributes means that the actual probability calculated by the Naïve Bayes classifier is inaccurate. It's not an actual statistical probability. So we cannot say that the resulting probability is the actual probability that an example belongs to a specific category. But what we can do is, however, to compare the results of example belonging to different categories and see which category has the highest probability. And the category with the highest probability is what's this input example most likely belongs to. And this works surprisingly well for many real-world classification problems. There's different versions of Naïve Bayes, and we'll first take a look at the multinomial Naïve Bayes algorithm. And it works best when the inputs are categorical or text. So let's start with an example. We create an example dataset, where we add another variable to our FIFA player dataset. So gamepad can be great, average, or junk. Stiffneck can be yes or no, and the play scale is good or bad. And here we have our dataset. So quite small dataset in this case. We have 4 examples of good players, and we have 5 examples of bad players. The first step is that we need to generate a frequency table from this dataset. So it looks like this. We have a gamepad, the stiffneck, and the player skill attributes or class. So first, the gamepad can be great, average, or junk, and we have the 2 categories, good or bad. And we look at the dataset and see how often is great in combination with good. And we see that occurs once. And the same great occurs once with bad. Great gamepad occurs once with a bad player. Average occurs 2 times for good players and 3 times for bad players, and junk appears once for both. Stiffneck appears 3 times, but we have, yes, stiffneck 3 times for good players and once for bad players, and no once for good players and 4 times for bad players. And the output class player skill, we have 4 examples of good and 5 examples of bad, so 9 examples in total. So that's the frequency table, and we continue by filling the table with prior probabilities. So we just keep working with the table. Probability of great given x. The probability of great happens once for good, and we have 4 examples of good, so 1 divided by 4. Great occurs once with bad, and we have 5 examples of bad, so 1 divided by 5. And we continue. Average happens 2 times for good, so 2 divided by 4, so we have 4 good examples. 3 times for bad, 3 divided by 5, since we have 5 bad examples. Stiffneck 3 times occurs for good players, 3 divided by 4, since we have 4 good players, in 4 examples of good players, and once for bad players, 1 divided by 5, since we have 5 examples of bad players. And the distribution is 4 divided by 9, 4 examples in total of 9 examples for good players and 5 of bad players. And this table with frequencies and probabilities is actually all we need for classification. So now we can answer questions like, a player has an average gamepad and a stiffneck, is he a good or a bad FIFA player? We have 2 possible categories, good or bad player, so let's calculate the probabilities of the above mentioned player belonging to 2 categories. So our task is to classify a player, gamepad is average and stiffneck yes. Probability that the player is good is calculated as probability of being good multiplied by probability of average given good and multiplied by probability of yes given good. And we just look up all these values in the table and we multiply these 3 values, and the result is 0.1667. And we do the same for the player is being bad, so probability of bad is 5 divided by 9 if we look at the table. Probability of average given bad is 3 divided by 5, and probability of yes given bad is 1 divided by 5. And we multiply these 3 values, and the result is 0.0667. So good has a much higher probability than bad, so we classify this player as being good, a good FIFA player. Another example, if we have gamepad great and stiffneck no, probability that player is good, probability of being good multiplied probability of great given good, multiply our probability of no given good. We just look up these values in our table, and the result is 0.0278. Probability that player is bad, probability of being bad multiplied by probability of being great given bad, multiply the probability of no given bad. Look up the numbers in the table, and the result is 0.0889. So bad has a higher probability than good in this case, so we classify the player as bad. And we can notice that the quality of a gamepad has very little impact on the classification of being good or bad. The stiff neck attribute has a much higher impact on the result. In many applications, it's better to return a don't know answer than a misclassified example. For example, in spam filtering, it's often desirable to avoid having non-spam emails end up in the spam folder than to catch every single spam message, because we don't want to look at our spam folder every day to locate misclassified non-spam messages. This can be solved by using a threshold. A threshold of 3, for example, means that the probability for the highest category must be at least 3 times higher than the probability of every category. Otherwise, the classifier is unsure. So in our examples, we used a threshold of 1, meaning that we always classify an example as the highest category, regardless of a difference in probabilities. So the examples using threshold, p given good, p given bad. When we did our calculations in the first examples, we have a ratio of 2.499. So with a threshold of 1, we will classify this example as being good. But if we use a threshold of 3, the ratio is less than 3, so we give a don't know answer instead. In the second example, gamepad great, stiff neck no, the ratio is 3.198, so even if we use a threshold of 3, we classify this example as bad. So this is quite useful if we want to detect the cases where we are not as sure. In the second example, we are very, very sure in both cases that this is bad, regardless of our threshold. So we can be pretty sure that this example belongs to bad. But in the first case, if we raise the threshold to 3, we don't really know. So we can test with different thresholds and find a good threshold, and we can quite easily detect the classification examples where we are unsure of the result. In the examples we have seen so far, we had 2 nominal attributes, gamepad, with the possible values great, average, or junk, and the stiff neck attribute with possible values yes and no. In text classification, we have texts to classify, and the text can be of different lengths. And to make this work with Naïve Bayes, we first have to convert the text contents of each document to a bag of words, meaning that we have long lists of each unique word in our dataset, and the bag of words approach means that the input is the number of times each unique word is found in a text. And then we have to count the frequency and calculate the probability for each word belonging to each category in a similar way as in the stiff neck example. So let's look at how this works. So we have a small spam or non-spam example dataset with 5 examples. Buy cheap Rolex, you want cheap Vicodin, that's our spam messages. Can you buy milk, want candy tonight, and gym tonight, that's our non-spam messages. And we remove special chars like a question mark and make all words to lowercase, so the unique words are our bag of words. Buy cheap Rolex, you want Vicodin, can, milk, candy tonight, gym. So that's all unique words in the dataset. Our first step is to create a frequency matrix of these unique words. So it looks like this. So here we have all our unique words. Buy cheap Rolex, and we fill in the occurrences of these words for our yes or no examples. So by occurred once in the yes spam emails and no in the non-spam emails. Cheap occurs twice for the spam emails, yes, and 0 times for the non-spam messages. And in a similar way, we continue with the prior probabilities. So we just fill in the probabilities. We had 2 examples of yes, 3 of no. So if we take the probability of by given x, so by occurs once for the spam examples, and we have 2 spam examples, and once for the non-spam examples, and we have 3 examples, so 1 divided by 3. Cheap, the probability of cheap given x, cheap occurs twice for the spam messages, and we have 2 spam messages, so 2 divided by 2, and 0 times for the no messages, and 0 divided by 3. And we just continue filling in these values in our table. So next we want to do some classification. So we want to classify the text by cheap candy and know if this is a spam or a non-spam message. As in the previous example, we calculate the probability for being spam or not being spams. So if we try the yes spam email, spam message, we take the probability of yes, multiply the probability of by given yes, probability of cheap given yes, multiply by probability of candy given yes. So probability of being yes multiplied by the probability of all the words in the message being yes. And we fill in the values, and we see that here we have a problem. We have a multiplication by 0 divided by 2. So regardless of what these actual other probabilities are, the result would always be 0. So we need to solve this in some way, and one way is to use the Laplace correction. In Laplace correction, we always add some constant value to each probability to avoid 0 probabilities in the multiplication. So if we use 1/3 as Laplace correction, the probability for being spam looks like 2 divided by 5, probability of giving yes. Here we don't add a constant, but we add a constant for all the words given the different categories. So probability of by given yes is 1 divided by 2, that's what we look up in the table, plus the Laplace correction 1/3. Probability of cheap given yes, we look up in the table, 2 divided by 2 plus the Laplace correction 1/3. And we calculate, and the result is 2.9. And for not being spam, probability no multiplied by probability of by given no and all the words in the message, and we just keep looking at the values from the table and add our Laplace correction, and the result is 0.089. So this message is clearly classified as spam in this case. So, by cheap candy, that's a spam message. Is this correct? The word that is most prominent in the result is cheap, which exists in 2 of 2 spam messages and 0 of 3 non-spam messages. So if cheap is not a good indicator for spam, we need more training data where cheap also appears in non-spam messages, because as it is now, cheap is a very strong indicator of spam messages, and that's why by cheap candy was classified as spam. So we need quite large amounts of data for text classification to be accurate. There are also other variants of Naïve Bayes. The approach described so far is the multinomial version. There are some other variants, mainly Gaussian and Bernoulli. In Bernoulli, we don't count the actual frequency of an attribute in a category. Instead, we use 1 if the attribute appears in any document or any example belonging to that category, and 0 otherwise. So we don't count the actual number frequency, we just use 1 if it exists, 0 if it doesn't exist. Otherwise, Bernoulli works similar to multinomial. In Gaussian, we assume that attributes are numeric and follow a normal distribution. So it's used when the inputs are numerical in contrast to the other variants that I use when the inputs are categorical or texts. So let's take a look at how it works. So we use a reduced version of the iris dataset in this example, where we only use the petal length and petal width, so just one of our leaves. And we take only some of the examples from the actual dataset, so a reduced iris dataset. So first step is to train our algorithms on the dataset. The first step in training is to divide the dataset into each category. We have two categories here. We have the Satosa and the versicolor. Then we calculate the mean value of each attribute for each category. So we just sum up the values for the attributes for each category and divide by the number of examples for that category. And we also calculate the standard deviation, how much each value differs from the mean of each attribute for each category. So we calculate the differences in values compared to the means, and we raise them to the power of 2, and you calculate the sum, and we divide the sum by number of examples minus 1. If we do this in code or in Excel or something similar, we fill in the data and we calculate the mean values. The mean values for petal length iris total 1.45 and the petal width 0.25, and the standard deviations, how much the values differ from the mean. I want to see that for petal width, for example, the values are fairly consistent with very small standard deviation. For iris versicolor, the mean for the petal length of 4.40 and petal width 1.40. So we see that the values are typically much higher for iris versicolor or iris setosa. But we have also a much higher standard deviation. So it's not as simple as saying as this has high values and this has low values, because we have quite large differences here. So this is actually all we need to do for training. And this is a very fast approach to calculate the mean and standard deviation of a set of values. During classification, when we want to classify new unknown examples, we need to calculate the probabilities of the input values belonging to each category using the Gaussian probability density function, or PDF, Gaussian PDF. So PDF takes as input the actual attribute, the input value, attribute input value xi, the mean values and the standard deviations for all attributes in the training set for this category. And we just use this quite long formula to calculate the Gaussian probability density function. And next, we multiply the probabilities for all attributes for each category. So we have calculated a number of PDF values for each attribute and category, and we just multiply the probabilities for all attributes for each category. And each probability is then normalized by dividing with the sum of the probabilities for all categories. And we classify the example as a category with highest probability. And as a side note, the Gaussian, or also called normal distribution, is available in many APIs and in Excel, etc. similar. So we might not need to implement the actual formula to calculate it. So if we do this, we take our example, go back to our example. So we know the mean and standard deviation values for both our attributes, for both of our categories. That's what we have learned from the training data. And we have an unknown example, a new example. So the petal length is 1.6 and the petal width is 0.8. So that's our input. And we want to know if this input is an indicator of being a setosa or a versicolor flower. So we calculate the PDF, Gaussian probability density function, either using the direct formula or using some function in our API or Excel. And we get these results. So 1.601 for being petal length and 1.970 to the power of minus 9, so a very small value. And we do similar for versicolor. And when we multiply both these together, so we get a probability for being setosa of 3.154 to the power of minus 9, and probability of being versicolor 2.776 to the power of minus 8. And if we normalize this by dividing this value with the sum of both p's for both categories, we get 0.102, and here we get 0.898. So the probability of this example belonging to iris versicolor is 0.898, which is much higher than the probability for setosa, so we classify this flower as an iris versicolor. The problem here is that the probability for each attribute belonging to a category is typically very small. And if we have lots of inputs, multiplying lots of small values can lead to numerical underflow. The system is unable to handle such small values when we multiply them together. We already had quite small values here. In this example, we have only 2 attributes. So the result could be 0 instead of the actual result. And we can fix this by combining the log of the probabilities together. So this is done by transforming the attributes x and y, or petal length and petal width, we take x and y in this example, as the natural logarithms ln x and ln y. And this is often called math.log x or math.log x, and the base math.e, Euler's number in programming APIs. And the next step is to perform the log equivalent to multiplication, which is actual addition. So instead of multiplying x and y together, we simply add x and y together. So here we avoid the problem of underflow, since we use addition instead of multiplication. And finally, we transform the equivalent product ln xy, so the addition of all these values, back to the original form by taking e, Euler's number, and to the power of this result here in step 2. And this operation is often called math.exp, and we fill and send in a value in programming APIs. So if we do this for our example, we have calculated the PDF values. That's what we have done in the previous example, and we'll continue by calculating the natural logarithm of the PDF values, and we get these results: 0.471 minus 20.045. And we calculate the sum of these ln probabilities, 0.471 and minus 20, and we get a result of minus 19.575 here, and minus 17.400 here. And when we take this sum e raised to the power of this sum, and we see what we get, the exact same result as in previously when we multiplied the attributes probabilities together. And if we normalize it, we also get the same result. So we get the same result, but we avoid possible numerical underflow. So that's usually a good addition when we implement Naïve Bayes. So to summarize, despite its simplicity, Naïve Bayes is often effective for text classification and numerical datasets that are not too complex. Since it's very fast, we can use it as a baseline to compare performance of other, more complex algorithms. So if we test it on some datasets, here we have datasets with a number of clusters, and we see that the Naïve Bayes is almost equally as good as the random forest, which is a very accurate algorithm in most cases. It clearly divides the different clusters. In the random forest, it also divides the cluster. We get slightly higher accuracy because here we have a misclassification. But random forest could also, we see that there's some indication of being overfitted, since the boundaries, especially for a blue class, is quite complex. So in this case, Naïve Bayes works really good. If we have other datasets that are a bit more complex, especially when they are not as well separated, like this one, the Moon's dataset, we see that Naïve Bayes has a bit of a difficulties to find good boundaries, since it only works with the mean and the standard deviation values of the two categories, and they are not as well separated into clusters in this case. So here we get an accuracy of around 93%, and random forest is able to learn this dataset perfectly. So depending on the dataset, it can work very well or work not as well. So we have to try different algorithms, because Naïve Bayes is very fast compared to, for example, random forest. So if it has good accuracy, for example in datasets such as this, we can benefit from using Naïve Bayes instead of more complex algorithms. So that was everything I had to say about the Naïve Bayes algorithms. Thanks for watching.